Hi, this paper addresses a visual correspondence problem by extracting discriminative local features that are invariant to imaging variations. We introduce a self-supervised learning framework, RELF, which utilizes group equivariant CNNs to extract rotation-invariant descriptors. Instead of relying on complex data augmentations, we employ an E2CNN framework to effectively learn rotation-invariant descriptors and their orientations. The output features and orientations are then processed using a novel technique called group aligning. This technique shifts the group equivariant features by their orientations along the group dimensions, achieving rotation invariance without losing discriminability. Our two loss functions enhance the group local features to be robust to geometric and photometric variations. In our paper, we have two main contributions. First, we introduce group aligning, which maps equivariant features to be invariant without losing group information. Second, we use an equivariant backbone network and two loss functions for self-supervised equivariant training of our model. The motivation of our paper is to exploit the group equivariant features to extract the invariant descriptors. For reliable correspondences, local descriptors need to be both invariant and discriminative. Classical local invariant descriptors are effective but not applicable to standard DIM networks. The classical methods use shallow gradient-based feature maps. They construct an orientation histogram by aggregating local image gradients, and they normalize the patchy descriptor using a dominant orientation in the histogram. Similar to this, we normalize our rotation equivariant features using the predicted orientation in our network. A learning method, RFNet, obtains local features by applying rotational data augmentation. RFNet may be lost to rotation, but it cannot be said explicitly equivariant or invariant to rotation. In the most similar work, GIFT, their proposed bilinear plane collapses the group dimension so the descriptor loses representation power. To achieve rotation equivariant representation, we employ a group equivariant network. This network utilizes parameter shared convolution to extract feature maps for all group actions. Existing pooling method loses the discriminative information, so we propose a method to preserve the group information. This animation shows structurally guaranteed equivariant features using E2CNN network. This is our overall architecture. We utilize rotation equivariant ResNet 18 backbone. We take multi-layer features and concatenate them to combine the information of low-level geometry and high-level semantics. After obtaining rotation equivariant feature map F, we assign local features to predefined key points. We use the Harris corner detector at training time. We allocate the local feature at P to each key point, which will transform to an invariant descriptor. We obtain an orientation map by selecting the first channel of F and allocate an orientation vector O to a key point. Using the group equivariant key point feature P and the orientation O, we conduct group aligning for invariant mapping. At first, we estimate the dominant orientation using argmax to the orientation vector O. The dominant orientation delta is used for group aligning of P. After group aligning, we flatten and L to normalize the invariant descriptor and obtain the final output descriptor D. The left figure shows the comparison of group aligning and group pooling. Our group aligning keeps the group dimension so it preserves the feature discriminability. In the equivariant orientation vector O, we can extract multiple descriptors by different alignments in the group dimension. This multiple descriptor extraction corrects first matches by compensating for incorrect orientation predictions. To train our network, we use two loss functions. The contrastive descriptor loss is info NCE form contrastive loss between source image descriptors and the target image descriptors. We also use an orientation alignment loss, which is proposed in the previous papers. we compare the source orientation histogram to the shifted target histogram using cross-entropy. For the experiment, we train our network jointly and conduct multi-scale inference. We train our network self-supervised manner by generating synthetic image pairs with geometric transformation and photometric jittering. We use 3 datasets to evaluate our method. At first, the Roto360 is used to evaluate the rotational invariance. To evaluate more general geometric transformations, we use the H-patches and MVS datasets. At first, we compare our group aligning to the existing invariant mapping methods. The left table compares the invariant mapping operations only while keeping the other conditions. Our group aligning achieves the best performance. In the left table, our method shows better matching accuracy compared to existing descriptors on the Roto360 dataset. The right figure illustrates robustness to rotation changes. This table shows transferability to general transformation. Our group aligning still performs best compared to the other invariant pooling methods in the fixed backbone network. With multiple descriptor extraction schemes, our group aligning can also increase the matching performances. Our group aligning performs better than the bilinear pooling of the gifts in the same backbone network setting. This table shows the ovulation study and design choice. Without the loss functions, the network is only equivariant to the rotation, so the generalizability decreases. To balance the trade-off between efficiency and the model's flexibility, we choose the order of group 16. Our model estimates more consistent orientations than LFNet orientation estimation. Our method finds more true matches, denoted by green lines in these extreme rotation cases. We evaluate the matching performance in the extremely rotated day-night image matching dataset. Our descriptor achieves the best performance under large illumination changes with extreme rotation. In conclusion, we propose a self-supervised rotation equivariant network and a new invariant mapping operation, group aligning. This is the end of the presentation. Thank you for listening.